we can begin. So I'd like to thank you all for coming to this UNM-PNM public lecture. We have this every year for the public and also for everyone that's participating in the second round of the contest. It kind of marks the day that they will have to take the exam, which they should have received over email this morning. So I'm very pleased to introduce Professor Peter Kuchment from Texas A&M University, who will be talking about the mathematics mystery. And if you don't mind, Peter, I will say a few things about you. So Professor Peter Kuchment is a University Distinguished Professor of Mathematics at Texas A&M University. His research interests include partial differential equations, mathematical physics, and integral geometry and their applications. He has made seminal contributions in areas such as computed tomography, which he talked about at UNM a couple of days ago, quantum graphs, differential equations, and photonic crystals, for which he was elected a fellow of the Institute of Physics, American Mathematical Society, American Association for the Advancement of Science, Society of Industrial Applied Mathematics, and the American Physical Society. He's also a senior member of the Institute of Electrical and Electronics Engineers. He is the author of over 200 papers and books and has delivered numerous lectures and lecture series around the world. He's also interested in enhancement of K-12 education and is the founding director of the Smart Summer Math Camp and also co-founded Texas A&M's Math Fest. And also co-directed a correspondence math program for middle and high school students at the Wichita State University in Kansas. He received his PhD in mathematics from Kharkov University, Ukraine in 1973, and his Doctor of Science degree from the Mathematics Institute of the Academy of Sciences of Ukraine in 1983. And we are very happy to have him here.
Thank you Thank you very much for this nice introduction and for invitation. It's my pleasure to give this lecture. I admire these activities that you have been running for many years. This is what universities should do more and more, and not that many do, actually. So thank you very much for doing this. Now, I know that this lecture is attached to some contest in mathematics, which means that you are solving mathematical problems, whatever you call them, problems, questions, puzzles. What I will be talking now is not about any problem in mathematics. I will be talking about problem with the mathematics. And this problem is still unresolved. I don't believe it will be ever resolved, and I don't plan to resolve it, but I want to attract your attention to it. By the way, mathematicians are usually, they are displeased when I talk about this, but everyone else shouldn't have this kind of feeling. So what is a mystery? I have met very few people who are exceptions, but most of us like playing intellectual games. For instance, chess, Go, checkers, Sudoku, whatnot. And you probably know that the number of different intellectual games is expanding exponentially. If you look them up, there are so many new games that you can purchase or play online. And what is common with these games is that we play with artificial objects, usually not with something from real life, except Monopoly when you have houses and fabric and industries, etc. But normally, like chess figures, you don't have rooks in real life. You don't have pawns. You don't have, we do have queens, but not the chess queens in real life. And the rules of game are actually completely artificial. There is no chessboard in real life on which real figures, chess figures move. And the rules are also artificially invented. And we play with pleasure, at least many of us, which excludes me. I somehow don't play chess. I know how, but I don't do this. I don't get a pleasure from that, but I have played quite a few card games with pleasure, which is the same thing, artificial objects played by artificial rules. So now, standard complaint about mathematics that it's abstract. I don't expect to hear this complaint from people participating in this lecture, since you're all apparently think highly of mathematics and don't mind it being abstract. But on the other hand, what does it mean abstract? It means that the objects that we deal with in mathematics, even those that are geometric, like points, true points don't exist. Straight lines of zero widths, they also don't exist. And if you go to higher levels of mathematics, you will see such objects that it is hard to even imagine them existing. We invent very weird things. And that's why mathematics is abstract. But the same thing is here. As I said, we invent some objects like chess pieces. We invent the rules how to play with them, and we get pleasure for doing this. And by the way, it is also abstract since those pieces can be made of anything. For instance, you can imagine Neanderthals playing the chess and the pieces made from bones, or which actually had happened before when real people were chess pieces. So, in fact, you can play chess without any pieces. You can play chess blindly. So it is as abstract as mathematics is. So what is the conclusion? The conclusion I want to make is that we are all mathematicians. Since it's very hard to find a person who doesn't get pleasure from playing at least one of those zillions of intellectual games. So ancient Greeks discovered, or maybe invented, there is fight about this, but I will not get into it. Ancient Greeks discovered that mathematics itself is a fascinating game of intellectual pleasure. Actually, Greeks were not alone. Ancient Chinese also did a lot of mathematics, and Indians. In medieval times, Arabs and Persians did a lot of mathematics, but as far as I understand, in ancient days, Chinese and Indians did mathematics mostly for some applied purposes. Greeks not only didn't do this for applied applications, if you read about Pythagorean school, they despised any applications. They would expel you if you do something applied, which was kind of too extreme. But it was pure game of intellectual pleasure for them, exactly like you do with backgammon or Go or other those games. So what is mathematics then? And Nobel Prize winner Eugene Wigner, whom we also will mention several times in this lecture, said the following, which actually repeats what I said before, but in more succinct form. That he says that mathematics is a science of skillful operations with concepts and rules invented just for this purpose. Like chess, the chess pieces and rules were invented for skillful playing with them, for nothing else. Well, so this is a game. But there is something different with mathematics. Among all those games that I listed, mathematics is unique. In what way? It is intellectual games that mathematicians play mostly for intellectual pleasure, but it works magic in physics, engineering, chemistry, nowadays even in social sciences, everywhere. And we learn this from school. And people have noticed this since ancient times. Archimedes said that there are things which seem incredible to most men who have not studied mathematics. It was almost 2,000 years ago. Then 1,500 years later, Roger Bacon, British philosopher, said the same in different words. Neglect of mathematics works injury to all knowledge. He who is ignorant of it cannot know the things of the world. Then it was repeated several hundred years later by Galileo. It's a very famous quote that the grand book of philosophy or nature is written, the universe is written in the language of mathematics. And then he describes their consequences for you if you don't know mathematics. So they all said this, and we were told about this in school, at universities, every day. But the question is why? Why is mathematics so useful? Why does it happen? And this is a question that mathematicians don't like asking. The reason is, I believe, is very simple. Every university has mathematics department. We teach mathematics to every single student. We get paid for doing this, for playing our intellectual game. There is no department of Sudoku at any university, I don't believe. There are not even departments of chess. Why? Since none of other games have this magical property, being useful everywhere. But so mathematicians probably think you don't trouble. Don't kill the goose who brings golden eggs. So we are paid for having fun, so shut up and enjoy. Well, it's not a very good answer, but I still want to discuss it. Not that I will give you an answer. No one has managed to do this. It's been discussed for 2,000 years, but let us look whether this is indeed true. Here is a crazy example. Conical sections. Actually, this guy, his dress is anachronism, since he's dressed into medieval dress. It should be something ancient Greeks. Ancient Greeks studied what happens if you take a cone, a spherical cone, and cut it with a plane. They studied conical sections. And what was the reason? None. You can hardly think of any applied problem, especially in ancient Greek times, when you need to know what happens if you cut cone with a plane. But they found it fascinating, and they discovered three major types of curves, so-called quadrics. Ellipse, this green one, if you tilt the plane further till it gets parallel to that line. Do you see my hand moving here? Okay. Then it becomes parabola for one instant. Then you tilt it further and it becomes hyperbola. Circles are kind of particular cases, the best case of an ellipse. Well, they studied this for no reason. It took just 2,000 years, and Kepler discovered that planets' trajectories are ellipses. Fortunately, he knew what ellipses were. He read ancient Greek geometry. Otherwise, he wouldn't be able to figure it out. He just observed from observations done by his teacher, Tycho Brahe, that those trajectories are not circles like it was assumed before. They are close, but they are ellipses. Well,
Peter, could I ask you a quick question?
Yes.
An anonymous attendee would like to ask, what is a hyperbola?
Well, I would have to draw it, and for that I would need to start. I can tell you. You probably know what is the graph of function y equals 1 over x. That's a hyperbole. It's unbounded.
There's also a vague picture of it at the bottom of this code, right? The orange one.
Yes, but it's hard to tell the difference between hyperbola and parabola here. Parabola is also unbounded, but parabola happens only at one instant when the plane is parallel to that line. Before it's ellipse, after that it's hyperbola. So to achieve parabolas is hard. Now, so in 2000 years of having this fun, the whole world of mathematicians had fun with this for no reason. It's just nice. Kepler discovers that planetary orbits are ellipses. Well, very soon Galileo discovers that trajectories of a projectile which you throw are parabolas. Then Newton kicked in. Using those things and something else, he derived his gravity law. And oops, all our contemporary science started. So my conclusion is that those insane Greeks looking at cutting cones by planes 2,500 years ago, they started all our science. So this crazy thing ended up being our contemporary science. This is not the only example. Even better example is number theory. Number theory, since ancient Greeks, has been considered as a queen of mathematics. For what reason? Since it is beautiful and hard. What else do you need? If the game is too simple, there is no challenge in playing it. So it's beautiful, hard game. Well, at the center of ancient Greek mathematics were prime numbers. What does it mean, prime number? If it can only be factored into one and itself. So for instance, these are prime numbers, and these are not prime since they can be factored. Well, if you start thinking about this, who cares how many factors does a number have? I cannot imagine why ancient Greeks would do this. There was no practical reason whatsoever. They just discovered that it is a very interesting question, that prime numbers are difficult, and therefore the game is nice. Well, the first applications of this thing appeared in the 20th century. But even those applications were not very natural. The first applications you probably know about, have heard about RSA codes. They are the main types of codes that make our internet, like bank transactions, etc., secure. It is based on some number theory theorems. But it is not very convincing example. Why? Since those codes have nothing to do with the nature. We invented those codes. And it's natural that when we invent something, we use what we already know. We had prime numbers, so we use them. However, strange thing happened at close to the end of 20th century. In 19th century, Riemann introduced so-called zeta function. I will not tell you what it is. And he studied properties of zeros, of roots of this function. He showed that behavior of those roots, there are infinitely many of those roots, is crucial for number theory. It is still being crucial for number theory. He formulated a conjecture which is still unresolved, and there is out $1 million prize for solving it. Why? No reason. It is just nice mathematical fun. You're saying I cannot do this? Am I a mathematician or what? I'm challenged, I'm working on it. Well, close to the end of 20th century, when people observed spectra of complex quantum systems, for instance, a very heavy atom or big molecule. You look at energy spectra, these are numbers, and it was discovered that in some sense that I will not explain, they behave exactly like zeros of the Riemann zeta function. So what is going on? Why quantum mechanical systems know about prime numbers? We don't know. But this is what is happening. Another example, also fascinating example. Quadratic formula for the roots of quadratic equation. It has been known since Babylonians. Unfortunately, not our university students now remember it, but it's a problem teaching differential equations. Somehow in schools, you are often taught to factor to find the roots. To factor arbitrary quadratic equation, you must be a genius like Euler. Normal people should use quadratic formula. So Babylonians already knew quadratic formula, and it was important since quadratic equations do arise in practice when you deal with areas of land, etc. Okay, the formulas for roots of cubic third order equation, Cardano's formula. It's called Cardano's, but as always happens, he was not the one who discovered it. His student Tartaglia discovered it. Cardano published it, and therefore it is called Cardano's formula. There is a formula for roots of cubic equation. It took about also a couple of thousand years. It was discovered only in 17th century, I believe. So the formula is pretty bad. Then at about the same time, the formula for the roots of fourth order equation was discovered by Ferrari, also in Italy at the same time of Renaissance. And what was the reason? Why did they want to do this? Frankly, no one uses those formulas even nowadays. If you look at them, you see that they are kind of horrific, especially for the fourth order. And we have we have had for hundreds of years, much nicer approximate ways to find those roots with arbitrary precision, etc. So why would they do this? The reason was to win contests. At that time, it was popular when some mecenat would offer a prize, a monetary prize. There would be a public debate contest between two scientists. They give each other problems, and who wins gets this money. Well, imagine that you are the only one who knows how to solve cubic equation. You give this to your opponent and you win, hands down. So these were the reasons to do this. And as I said, the formulas are awful. I have never seen them used, and I don't believe they are used. But it was done for this. At least there was practical application to get some money. But people wanted to go further. What about the fifth order equation? For a couple of hundred years, many people tried, no success. Well, again, who cares about formula for roots of fifth order equation? It's even less meaningful than for cubic and quadratic equations. Well, no success, and then the reason was discovered. Such formula does not exist. It was proven by three people about the same time in different manner, and their combined work is still, as I will mention, very important, by Abel, Norwegian mathematician, Galois, French mathematician, and Ruffini, Italian mathematician. By the way, stories of life of Galois and Abel, who both died very young. Galois was less than 21 years old, and Abel was 27. You might want to read their life histories. They're very interesting. So they proved that there is no such formula. Again, who cares? We don't need this formula anyway. There is no formula, that's it. However, doing this useless thing, fighting this intellectual challenge, they developed a technique to prove that there is no, and this technique is called group theory. Even in mathematics, it took about 40 years after Galois's death to absorb what they did. So, okay, they invented this group theory. So again, why do we need it? It's just fun theory. It can do a lot. And for about 100 years, it was considered by many, including physicists, as this crazy thing that mad mathematicians do all the time. So who needs it? Well, 100 years ago, quantum mechanics came about. And it was discovered that group theory is one of the main things that are needed there. In quantum mechanics and high energy physics, studying elementary particles, etc. Now the group theory is everywhere. This is just propaganda. I show you the covers of 3 books, one on physics, one on chemistry, and one on image science, imaging. All of them have group theory as a major part. The first 2 even have group theory in the title. The last one doesn't, but it's 1,200 pages book, Foundations of Imaging Sciences and Science, and big chunk is about group theory. Okay, another example, matrix algebra, done mostly in 19th century. Well, what is a matrix? It's just kind of you arrange the results of competitions, etc. It's a table. Mathematicians developed some algebra with those tables. Well, there are many things that mathematicians do. Who cares? Again, in 1920s, when quantum mechanics was being created, Werner Heisenberg, future Nobel Prize winner, who one of the main creators of quantum mechanics, was doing some pretty awful complicated calculations. And Max Born, who was his colleague, and who was a rare physicist who knew about matrices, he looked at what he's doing and he said, Werner, do you know what you're doing? You're doing matrix algebra. What the heck is matrix algebra? Since then, you cannot do quantum mechanics or many other things, including even economics, without matrix algebra. Another example, knot theory. What is a knot? I will not explain. You see a picture of a knot. And you know that knots can look more or less complicated. You can deform a knot and it will look much more complicated. So what does knot theory do? In particular, one of the main things is you looked at 2 knots. Can you say that they're truly different, or one is just bad deformation of another? Why was it started? In 19th century, there was an idea, I think Lord Kelvin had this idea, that different knots, at that time, there was no knowledge of what are electrons and even what atoms were. Since ancient Greeks, we believed that there were atoms, but what they were, no one knew. It was clear that there are different atoms of different chemical elements, and it was suggested that maybe different atoms are just different knots. Well, in 10 years, it was discovered that it was wrong. It doesn't explain any physics at all. It's a wrong model. It's a beautiful thing, but it's absolutely wrong. But mathematicians stuck with this. It's a very interesting problem. Actually, it still hasn't been resolved completely. There is major work done by them. Why mathematicians were doing this? Since it's a very interesting and difficult mathematical puzzle. Well, In the last decades, nodes came back with vengeance, including in physics. So look, what is the conclusion? Conclusion about mathematicians. What mathematicians do? Mathematicians are mad hatters. They do weird things. They build some ladders to nowhere that they want to climb. Those challenges, mathematical challenges. Why? For no reason, since it's difficult and therefore challenging and therefore interesting. Well, and our example shows that very often, not always, but often, we suddenly discover that this ladder to nowhere leads to some previously unsurmountable mountain in physics, in chemistry, elsewhere. So we were climbing it just for the fun of it. Actually, the truth is that every researcher, not only mathematician, should have fun doing what he or she is doing. Otherwise, it will not work well. Not only researcher, probably to do any job well, you need to have fun. So mathematicians have very strange sense of fun. They were climbing those ladders leading nowhere. But if you live long enough, for instance, 2,000 years, you discover that what you did solves this problem. If you're lucky, it might happen in 50 years. Nowadays, it's happening much faster. But again, so this is the mystery of mathematics. We are doing some kind of, we're playing strange game with our mind, with artificial objects that we invent. And if you go further in mathematics, you will see how artificial and strange they are. We invent the rules, we play them, and then, oops, for whatever reason, it's useful. Not that it's always useful, I am not claiming this, but surprisingly frequent, the fact is that eventually it is useful for something, unlike chess or Sudoku. Another example is more than 100 years ago, mathematicians did some analytic work, solved some analytic problems that came from nowhere. It was not needed for anything. A pretty famous mathematician Radon suddenly thought about this problem and solved it. I will not tell you what it is. And when he passed away in memorial services, his work was not even mentioned. He's done so many good things, and this is, well, he was a little bit insane doing this. Now, the problem he solved is the basis for those wonderful CT scanners that discover cancer and other illnesses and save countless lives. So, in particular, what I want to emphasize, when you do mathematics, don't ask the question, what is application of this? If you are ignorant in mathematics, if you don't know much, you can invent problems that don't make much sense. But if you're already someone educated and you find a mathematical problem that is challenging and you feel that you should solve it, that's a good enough reason. You should be aware that you might not get job for that. You might not get tenure or salary. You see, not everyone lives 2,000 years to see his or her ideas being useful. But this is for mathematicians, this is the idea. Now, why does it happen? Why our long chains of thought? We follow some logical rules that we invented, and they have nothing to do with reality. How come we come up with things that could eventually become useful? And you saw amazing examples of it. We don't know. Look, our brain can invent absolutely crazy things. So just in terms of chances, most of the things that we crazily invent in our mathematical head should be useless. Well, it's not what happens. There are useless things that we invent in mathematics, at least now, but surprisingly many are useful eventually. Why? We don't know. Then another thing, okay, what does applied mathematician do? Mathematician takes the data from the nature, builds up some mathematical model, then we use our logic to proceed. We came up with some conclusions due to all the laws that we use in our brains that we invented ourselves. Then we give the practitioner's prediction. If you do this and that, the following thing happens. Well, why should the nature follow our logical predictions? Why should nature care what we did in our brain with practical data? Why should it, in many cases, follow our predictions? We don't know. Well, it's not always the case. You might think from after examples that I gave you that it's always like this. Mathematicians invent something absolutely abstract, and after 2,500, or if you're lucky, 50 years, it becomes useful. No, there is a lot of mathematics that actually does come from applications. We develop some mathematics due to applications. But again, the question remains, we build those mathematical models and study them using our own laws of logic, and then give the prediction why should nature follow them. So even when the mathematics arises initially from the real world, it doesn't justify why our results, completely brain results, agree with nature, or nature agrees with it. And certainly you might think, you might understand that I am not the only one asking this question. As I mentioned, mathematicians usually avoid asking these questions, but physicists and philosophers, naturally that's a philosophical question, do ask this. For instance, Albert Einstein said that the most incomprehensible thing about the universe is that it is how comprehensible. And this is not even about mathematics. What he asks is why there are laws of nature that we can comprehend and then predict something. It doesn't have to be like that. The nature could have been completely chaotic. For instance, why is there a mechanical rule that predicts you that if you throw a projectile in this direction with that speed, then it will follow the following trajectory? We could have lived in the universe where every time you do the same, but the trajectories are completely different. So this is a question. We don't know the answer. And concerning mathematics, he says exactly what we are discussing, that mathematics is a product of human thought, which is independent of experience. Why is it so appropriate to objects of reality? Wigner, whom I already quoted, he also said that he was among the first in contemporaries who started discussing this. He says that the enormous usefulness of mathematics in natural sciences is something bordering on mysterious, and there is no rational explanation of it. Then he followed that the miracle of appropriateness of the language of mathematics is a wonderful gift which we neither understand nor deserve. So we don't know why. But it's a wonderful question. Now, there are brilliant writings about this that you would enjoy reading. The first, as I said, the famous paper by Eugene Wigner, The Unreasonable Effectiveness of Mathematics in the Natural Science. You can easily find it on the internet. There is a beautiful book by Mario Olivier, who is physicist. Is God a mathematician? You see, this is he asked actually the same question. Why does mathematics get any use? Roger Penrose has nice YouTube presentation where it's called Is Mathematics Invented or Discovered, which is closely related. Do we really invent all this, or we discover what is already there, and that's why it's applicable? Max Tegmark, who is physics professor at MIT, wrote Our Mathematical Universe. It is less simple reading, but it's also discusses the same question, and not completely related. A very nice little book by famous mathematician Jacques Hadamard, The Mathematician's Mind. He discusses a little bit different thing. It's about psychology of invention. How does it happen that ideas come to us? And he not only discusses this in mathematics, he even discusses this in poetry. Now, if this is completely arbitrary what we do in our brain, if it were, we would have produced a bunch of completely useless stuff, which we normally don't. So what are the criteria to distinguish good stuff from bad in mathematics? And the leading principle is beauty. It's like in music. What distinguishes beautiful music from ugly? And it sounds beautiful. Good music sounds better. What distinguishes good painting? It is beautiful. It's hard to quantify beauty in arts, and it's also hard in mathematics, but look, it's also criterion in art, in music, in chess, beautiful game. Someone who doesn't know chess cannot understand what does mean beautiful game. They move those pieces. So what's beautiful about this? Not everyone understands beauty of music. Not everyone understands beauty of architecture, but these are the main criteria there, and this is the main criterion in mathematics. This is cartoon where one mathematician wrote some proof, and another says, it's an excellent proof, but it lacks warmth and feeling. And that's not a joke. We say this in mathematics. And it's hard to explain, but I can show you what is a beautiful proof. These two pictures, you might, as participants in this contest, I believe many of you have seen those. They are proving, they are ancient Greek pictures that prove simultaneously two things. They prove Pythagorean theorem and prove Newtonian binomial formula. Just cutting one way and then rearranging pieces, you get both. That's a beauty. I don't know how Percier do more than that. Now, beautiful formula. The most beautiful formula, as most people believe, is the Euler's formula. E to the power I pi plus 1 is 0. What is beautiful here? Well, I will tell you what is. There are four numbers involved, E, I, pi, and 1. 1, you understand, it comes from counting. 1 apple, 1 cow, 1 chair. Pi is the ratio of the circumference of the circle to its diameter. I is this ugly imaginary unit, square root of -1. We invented it. It doesn't come from counting. It's not a real number. We invented it since we didn't like the fact that not all quadratic equations have solutions. With I, everything has solution. And E is even weirder. If you have dealt with the Euler constant E, 2.71, etc., all ways of introducing it are kind of involved. It's something about calculus. All those four guys, they live on different planets. They shouldn't know about each other. They shouldn't have any relation. Look, this short formula tells us that all these four creatures are closely related. And so the main beauty, not only in mathematics, but in all kinds of research, is when the two things or more that shouldn't know about each other happen to be the same. The borderlines between things that come from different worlds, this is the most exciting when you discover it. And there are certainly ugly formulas. There is ugly mathematics. So this is, you see, this is an ugly calculation. You can agree without seeing any details that it's extremely ugly thing, especially since this professor who checks it finds that the error is at the very beginning. Now, more about beauty. Maxwell, the genius who has done many things in the 19th century, he also created contemporary theory of electrodynamics, which deals with electricity and magnetism and light and everything. And the bottom line of this whole theory is these two equations. I will not explain to you any of those notations. But look, isn't it beautiful that two equations which actually look pretty much similar, E is electric field, B is magnetic field, even without knowing what this nebula sign is, what c is the speed of light, what d2 dt squared is, its second derivative with respect to time. Even without knowing this, you see how one equation encompasses the whole world of physics. Radio, for instance, light propagation, etc. So it's beautiful. By the way, Maxwell didn't write this in this beautiful form. His equations were ugly and huge system of ugly equations, and you needed to be a genius as Maxwell to be able to handle this, especially to invent this. In this beautiful form, it was rewritten by the famous and unfortunately not well-known electrical engineer in the end of 19th, beginning of 20th century, Oliver Heaviside. He was the creator of contemporary electrical engineering, and he was the one who wrote Maxwell equations in this beautiful form. Another example of beauty, Paul Dirac, another member of this group of young geniuses who were creating quantum mechanics. He wanted to write relativistic, I will not explain what it is, equations that describes electrons. Electrons were already discovered by that time, not that long before, but they were around. And he wrote an equation. It was very succinct, beautiful equation. There was one problem. It had two solutions. One corresponded to electron, and another didn't correspond to anything. So what would you say? Oh, trash this model. Dirac believed that such a beautiful equation, which has one solution, electron, should make sense. And he was right. Some years after that, positron was discovered, which was the second solution. A Nobel Prize was given for that. And Bertrand Russell, the famous philosopher and mathematician, also claimed the same thing that, by the way, he got Nobel Peace Prize, Bertrand Russell. The same, that there is a beauty in mathematics. Well, don't exaggerate too much. Don't go overboard. there could be beautiful theory which is completely bogus. Kepler, the same Kepler who discovered ellipses and Kepler's laws, he thought at that time there were 5 planets known. He somewhat describes the properties of their orbits through Platonic solids. It was beautiful, but it was completely wrong. Those Platonic solids had nothing to do with those orbits. And the last thing, that last mystery, which is somewhat of different nature, I want to describe, is about probability theory. There is something different about probability theory. Probability theory is based on experiment, unlike the rest of mathematics. Namely, people playing cards notice that frequencies of appearing of some random event stabilize if you do this many times. Like, for instance, if you have an honest coin and you flip it thousands of times, then the frequency of appearance of the tails and heads, they both will come closer and closer to 1/2. There is no reason for this that we are aware of. This is experimental observation. And this frequency to which, this limit to which the frequency stabilizes, is what we call probability. If not this experimental observation, there wouldn't be probability theory. You couldn't have it. And you see, it's different. Here, the mathematics comes from experiment. Without experiment, you wouldn't have guessed it. And finally, thank you very much for your attention. And that's all I want to present.
There's more people clapping, but you cannot hear them. Thank you very much for the very nice talk. And many people are clapping in the chat, I think. So if anybody has a question, please use the Q&A feature to type it in, and then James and I will either ask it for you if you'd prefer, or even better, we'll turn on the video and audio for you so that you can ask Peter directly. And maybe we'll give you a moment to write down your questions, and maybe I'll ask the first question just in case.
There is a question: do mathematicians discover things based on things other mathematicians? I don't actually understand the sentence. Other mathematicians discover, or what?
I think what they meant is whether mathematicians use other mathematicians' results when they are doing the research.
Constantly. Also, you have to acknowledge that you use someone's result, otherwise you're ostracized.
And then also Iris wanted to ask whether the Greeks really did do all of those things for fun, all the things that you described, because it just seems so over the top.
Yes, there is no question about this, since they didn't make any secret of this. Moreover, in Pythagorean, it was different for different Greeks. For instance, Archimedes, as you probably know, was very much applied person. He built machines, he did mechanics, etc. But for instance, he contributed a lot, but he didn't start this big thing. Pythagorean school explicitly despised any relation to the real world, since it is so pure that you shouldn't spoil it by practical things. So I think it's pretty much understood that all these Euclid elements, practically all, came just for playing with this. It was challenged, so why don't?
Makes sense. Dan also has a question, but unfortunately my Zoom keeps crashing, so I'm actually not seeing them anymore. But James, maybe you could take over.
I can read the quote from Dan. So it's in quotation marks. So I'm not sure if it comes from somewhere else, but he wrote, once when I was a student struggling to understand modern algebra, I was told to view mathematics as an intellectual chess game. I was ill-served by this bit of extemporaneous advice and vowed never to perpetuate the falsehood that mathematics is purely or primarily a formalism.
So this was the beginning of Charles Pinter's book on algebra, according to
okay. So I'm not sure that there's a question in there. I guess the question is, what's your response to that statement?
Well, I provided the claims for this statement. I provided quite a few examples when mathematics was developed for no reason at all or for bad reasons, like why do you need formula for the roots of fifth order equation, or even for cubic or for the fourth order equation. The same about conical sections. There are zillions of examples. Well, I should acknowledge that not every mathematician thinks this is a problem. But you see that many physicists think that it is a problem. I am among mathematicians who think that there is a big question mark here. I don't know the answer. Mm-hmm. But I personally do a lot of applied mathematics, a lot. But I do it since I find the problems arising intellectually challenging and exciting. I have done a lot of medical imaging. There is no question about being applied. When I did the first time just to add a little bit butter to my piece of bread by contract with industry, I thought, okay, so let's try to do this. It must be boring. I haven't stopped doing this for 30 plus years. Why? Since mathematics is absolutely beautiful and things that it also saves lives, it adds a lot to the pleasure. But my impression is that all science is done. I don't think you can do good science since you are paid for doing this. You have to be having fun, intellectual fun. However, the problems in most sciences come from practice, and you have fun doing those. Mathematicians are special that we can have fun without any practical application. It's just challenge. And again, there are different schools here, and I just presented this. I don't believe even people who disagree with mathematics being that removed from life can provide any good arguments for it being not removed. If you have dealt with any highest level mathematics like homological algebra, non-commutative geometry, etc., you might not even have heard those words. It is so abstract, and it was developed explicitly for absolutely abstract reasons. And nowadays, you know what? These are the main tools for studying very novel materials, so-called topological insulators, that were discovered very recently. They have amazing properties, and to explain them, we need all this heady stuff that was developed. Why? I don't know. But it is the truth. So I don't want to argue with people with other point of view. I just presented the view that most physicists whom I know think, at least I quoted famous physicists, several Nobel Prize winners who were insisting on this. And these were all very mathematical physicists. Einstein's work was differential geometry. Wigner's work is used in mathematics all the time. He's done wonderful mathematics. And he was the one who was wondering this. So I'm another who is wondering, but I'm not neither Wigner nor Einstein. So I know that there are opposing views, but I'm not going to argue. I just gave you examples that I believe are astonishing.
I think it's really good to see both sides.
Mm-hmm.
There's a question by Erica, and Erica, I'm going to promote you to a panelist so that you could ask it. You don't need to turn on your camera, or I could read your question if you prefer, but just in case, I'm going to promote you to a panelist, and I'm going to allow you to talk. So I wonder.
Can you guys hear me?
Yes.
Yes.
Yeah.
But now we can't hear you.
Sorry.
Now we just heard you. Now you're muted again.
Sorry.
Okay.
Can you guys hear me?
Yes, go ahead.
My question was if the physics that like the equation that was done back in the day that like nobody knew about, do we use it like in these days?
Like the equation for the quintics and the
For the quadratic or something like that.
Or
really not quintic.
The equation that nobody knew, and he would just like
we know.
just, like get the money or whatever because nobody knew how to solve it.
I don't quite understand the question.
The Riemann zeta function. So that was attached to a price. Is that what you mean, Erica?
I think whenever like they would do like those like competitions where you would give like the equation to the other person, and if they couldn't solve it, like you would win their money.
That's the Cardano, and the Tartaglia.
Yes, that was the reason why they were hunting for those formulas to win competitions. Certainly there was some pure intellectual challenge there as well, but they were doing those competitions. So it was, I believe, very strong input for finding those.
Well, according to that, that part of the lecture you gave, do we actually use that formula right now in these days?
You see, theoretically we need to know the roots of such equations. For instance, they describe behaviors of some dynamical systems, etc. Like when you study, for instance, ordinary differential equations, there are so-called characteristic equations, and the roots tell you how solutions behave. But unless it's quadratic, where we have the simple formula, the solution is we have so many wonderful ways to calculate the root, to find the roots, not explicitly, but approximately, with very good approximation. Newton was the one who invented some of those methods, that we actually don't need explicit formula, since explicit formula is not always also useful. It might be hard to compute well, even on computer. So we do need, those roots are extremely important, but explicit formulas, which unfortunately even don't exist, but even if they existed, this is not how we do this. This is not computationally friendly. You see, I don't believe there is difference between pure and applied math. But still, there are cases when pure mathematicians says, here is the formula, so go ahead and shoot from it. And applied mathematician says, oh, it will not work. it will bring so many errors due to computer precision and many other things that it's not going to work. And both will be right. So again, the answer, do we need those rules? Yes. Do we need those explicit formulas? No.
Okay, thank you.
So that,
I
does that answer
understood
your question?
everything. Yeah, that actually like answered the question and as to why like it's not used.
I missed, did I answer this question or?
Erica?
Yes, you did answer my
Okay.
question. Thank you.
In some classes, I tell students that here is your formula, but you will never be able to do this, since errors in your measurements will kill your solution. So
I think Kaden has a question on maybe in some sense a work-life balance. So Kaden, would you like to ask your question, which we can also see in the Q&A? Okay, maybe I'll read Kaden's question in the meantime. And the question is, can you play the guitar?
yes, I see this question. Yes, but it's my secret weapon. If my guests overstay their welcome, I start playing guitar and everyone leaves. So that's how I use it.
Okay. And then there is an anonymous attendee that's asking, do you have an opinion on how progress happens? Is it incremental when we build in others' works, or very disruptive when a completely unseen discovery or invention is made?
Oh, that's a very hard question. But at least in exact sciences, I believe the way the progress works, at least in physics and mathematics, it doesn't unseat everything we knew before. It finds boundaries of applicability. Einstein's theory didn't unseat Newton's mechanics. It just showed that there are limits when you can successfully apply Newtonian mechanics, and beyond those limits, it starts giving you bigger. So I think it's just gradual. It's very rare that you just throw away what was suggested. Like example is when someone thought that atoms are knots. This turned out to be completely wrong.
I think that answers it quite well. So probably like many things in life. So I have a question in the meantime, in case more people want to ask. So Richard Feynman had this famous story where he was modeling the spinning of plates or something, which led him to think about, I think it was electron dynamics and relativity, and eventually it led him to a Nobel Prize. I was wondering if you ever had some experience in working something quite abstract, and then some years down the road, or eventually realizing, this has a very great application. I know you kind of went between fields a few times, so.
Not really. I'm not a physicist. I'm a mathematician. So some things that, some things that I worked for 10 years on for no reason whatsoever, then happens to be important. I didn't know about that, but physicists invented a new scanner, new medical scanner. And what we were doing for no reason for 10 years happened to be exactly what was needed for that scanner. So,
well, I think that's exactly a good example. What kind of scanner was it?
It is so-called thermoacoustic tomography, and we worked just for fun for 10 years before that on the problems that turned out to be the main mathematical problems there. But we did this just for the heck of it.
That's very cool. So we have one more question from an anonymous attendee. And it is, what are you excited for in the field of mathematics for the future?
Sorry, could you repeat, please?
What are you excited for in the field of mathematics for the future?
Someone, it's attributed to many people, including Niels Bohr or to Yogi Berra, that it's hard to predict, especially the future. But what I'm excited about is that the mathematics used to get more and more splintered. People were doing differential equations or graph theory or approximation theory, and they couldn't, very frequently, they couldn't even talk to each other. While in 19th century and beginning of 20th century, mathematician was a mathematician. All big mathematicians could work on everything. And these days seemingly were gone. Now we witness new unification of mathematics, when completely things from different planets, and I told you, this is the most exciting thing that is happening now. You have some discrete problems that have nothing to do with differential equations or with some other areas of mathematics. They happen to be about the same. And there are young mathematicians. It's too hard for old people like me to catch up, but there are young mathematicians who have bird view. They are mathematicians. I'm not an expert on this. I can do anything. And this is an exciting time in mathematics. Extremely exciting. But where it will go further, I don't believe anyone can predict.
Okay, yeah, thank you. And I think there is a follow-up to this one, and I can suspect what your answer will be, but another anonymous attendee is asking, will there ever come a point to where there is nothing left to discover in the field of mathematics?
Since mathematics is very good at creating new, absolutely abstract objects, so there is no end to this. We can make them more and more abstract. But in general, I believe it's Newton who said that with the increasing radius of known, the circumference of the boundary between known and unknown also increases. I don't believe there is end of story for anything. I am actually not sure that this sacred grail in physics theory of everything is possible. It would be dull if you had theories that explains everything. So I don't believe this.
This reminds me of a proof you told me once about whether there is a least interesting number, and you said let n be the least interesting number. Well, that's interesting. So kind of.
Yeah, that's a very interesting feature that it is the least known. It's about non-interesting numbers. So if there are non-interesting numbers, there is the smallest non-interesting number. But then it's very interesting.
Right. So we didn't put this problem on the contest, but still a good proof to keep in mind.
Okay.
So
shouldn't they go to contest already? No, it's not exam time yet.
And it will be in 45 minutes. So unless there is, if there is any last minute questions, we're happy to answer them. Otherwise, we will let everyone go have lunch.
I'm available. So if there are more willing to ask questions, I'm. Yeah.
And Peter, if you don't mind, we'll post the recording of this also publicly with your slides.
Okay.
So people can revisit them and glean some more knowledge. I guess the last comment is that Dan suggested that we should have given up after creating negative numbers in the chat. I don't think he meant it.
Well, look, it is misunderstanding. Then we should have given up in creating any numbers, since if you think that negative numbers were complex numbers are abstract or negative numbers are abstract. Any number is abstract. Number one doesn't exist in the nature. You cannot show me one. You can show one apple, you can show one chair, one elephant, but there is no one. One is the feature that is common between all of them. And as far as I know, there are cultures that never developed the notion of one. And they stuck with one chair and one apple, etc. So since we got used to those numbers, integers, so much that we think they're natural. No, they're as abstract as imaginary unit.
Okay, so there's one very fast question. In terms of last year's shirts, what should we do if we haven't received ours yet? Just email the contest email and we'll send you a replacement shirt. And then Erica, you had another question.
I haven't received any shirts.
Well, you haven't received this year's shirt, so that will come. And then Erica, you had a question. So if you'd like, you can answer it live, or I can read it.
My question was, how did you decide to become a professor of math? Was it something you suddenly decided, or was it something you gave thought to?
First of all, I have never decided to become a professor. I just like doing mathematics. When I was doing this, I didn't know what will become of me. I never thought about positions, occupations, etc. But actually, I was supposed to become a sculptor. But in my high school, I had such an amazing math teacher that he made me a mathematician. After him, I couldn't think of much more than that. Actually, it's not exactly true. I wanted to be an astronomer, which is very mathematical, but I realized that my understanding of physics, in spite of winning in physics Olympiads, was insufficient. And astronomy is not just math, it's math and physics. So I went to mathematics. I never regret it, but I never thought about myself as future professor. I just like solving problems.
That's cool. You just went with like the flow of whatever happened with what you liked.
Oh, I think anyone should do what he or she likes doing. If you do something that you don't like, it's not very good life, no matter how well you're paid. Just going with what you like not always brings you jobs, money, etc. So unfortunately, that's the world. I was lucky that I like not solving Sudoku, but doing mathematics. So I can get paid for doing what I like.
Although it's also worth mentioning that if you're interested in mathematics, like we learned in the last year lecture, there's also a lot of kind of math-related jobs that you can do, like data scientist or actuary or. Well,
in fact, in Germany, this is unfortunately not the case in the US much. But in Germany, many people who got PhD in mathematics are grabbed by industry, left and right, hired in industry. Not since they do something that is needed in this industry, since they know that, you see, if you go to a new field, it's completely abstract to you. You have no clue about it. And mathematicians are the ones who learn to work with abstract things. So mathematicians are known, not all of them, but I would say majority, to be flexible, to get used to new notions, new environments, new procedures. That's what we do as mathematicians. So I had students who went to anything. I had students with whom I wrote even a paper when he was undergraduate. Very good mathematician. He is now a neurosurgeon. So it never hurts. Having such flexible mind, it's good for anything.
I think many of the students that went to your math camp ended up not being mathematicians, but being quite successful
Oh, yes.
other things. Like
Yes, and I
lawyers.
never tell students at my camps that I never entice them to go to this or that area. I tell them, go to the areas that you like. Some of them are doing linguistics, some are medical doctors and whatnot.
So unless there is any other questions, let's maybe thank Peter one more time. He cannot see you, but I'm clapping on everyone's behalf.
My pleasure, and thank you for questions. I love questions.
Yeah, and so there are some thank yous in the chat. And Peter, you might be, I think we had something like 90 or 80 participants today. And you have to multiply that by that, correction of multiple people in a chat. So it was, very nice to have
Yes.
everyone here.
That's a huge audience. I don't know whether I've ever had that many in any of my lectures.
Yeah, this is the power of Zoom, I guess.
Oh, in some undergraduate classes, I had like 100, even 200.
And then for everyone that's participating in the second round of the math contest, good luck. And if you've not received an email from us yet, please send an email to the UNM-PNM email address, and we will send you a replacement link.
Good luck with competition.
Yes.
Bye.
Bye, everybody. So I'm going to hang out here for a minute so everyone can exit, and then I'll shut it down. This way you can also see the stream of thank yous in the chat. Okay. Okay. I think probably we can finish it now.
Yeah.
Okay. Bye, everyone. Thanks for coming.